Hey everybody. Today we're going to be talking about how to conduct a one-way analysis of variance test, or also called ANOVA. So we've got a set of data here. You can see that there's 24 participants, and the variables we're particularly interested in are the eyewear variable. You can see that it's a categorical variable and it has three different levels. People who are wearing glasses, people who are wearing contacts, and people who don't wear either glasses or contacts. We'll skip over employment and education, and then we've got a couple of numeric variables, sleep and screen time. So in a one-way analysis of variance, basically you're trying to figure out if the means of some dependent variable, let's take screen time first. Okay, so screen time is going to be our dependent variable, how much time people spend on various screens per day. Or I guess this would probably be per week. I don't think anybody wants to spend 23 hours a day, or some people might. Um, and what you are looking for in a one-way ANOVA is differences in group means on screen time between basically three or more groups. And we conveniently have in eyewear three different groups: people who wear glasses, people who wear contacts, and people who wear neither. So we're going to see if, for instance, people who wear glasses spend more time or less time on screens compared to people who wear contacts or neither. That's what we're going to get into today. And then on your own, I'm going to have you do similar thing for these different groups of people looking at sleep. So let's dive in. What you can see over here is where we're headed, basically. With the one-way ANOVA, you're conducting what's called an F test. And how you do that is basically going to be between groups variance divided by the within groups variance. Okay. Now you can break those things down further. The between groups variance, which is also called the mean squares between, can be calculated as the sums of squares between over degrees of freedom between. The within groups variance, also sometimes called the mean squares within, is the sums of squares within divided by degrees of freedom within. Now, you could calculate all of these things by hand using just the numbers and categories that we see here. It would take quite an awful long time. And thankfully, we don't have to do that. So in one way, this is actually going to the next couple of chapters are maybe even going to be slightly easier because we're going to have R, an R Studio, do the hard work for us, and we're going to focus on how to interpret the output and how we actually go about conducting the analysis. So let's get started. I've taken all of these data and I have imported them into RStudio. So you can see it's the same data right here. And we are going to conduct a one-way analysis of variance for people who are in different groups, categories of eyewear, and their screen time to see if those groups significantly differ from each other in average screen time. So the first thing that you want to do is you need to build a model, okay? It doesn't matter what you name it. You could name it whatever you want, whatever makes the most sense to you. You could name it something like, you know, eyewear one or screen time one or your best friend's name or whatever you want to name it, right? You could put like, I don't know, maybe I'll put eyewear one. Maybe we'll just start with that. This is just the model, okay? So it doesn't matter. This is just the name of the model we're making. And then you put in basically a little arrow like this, okay? The less than sign and then the subtraction sign. And then you're going to input the function for an ANOVA test, which is called AOV. Within AOV, you put some parentheses, you need to specify your dependent variable and your independent variable. So the first thing that I'm going to do is my dependent variable, which in this case is going to be screen time. And how to specify screen time, you need to basically start typing in the name of your data frame. In this case, it's called ANOVA underscore example. And then I put a dollar sign, and that's going to tell are, hey, I'm talking about a specific column of my data set, my data frame. And in this case, the dependent variable is screen time. So that's what I'm interested in. Then you put a tilde, a little squiggly tilde, and then you put your independent variable. In this case, it's going to be eyewear. And you want to make sure that whatever independent variable you have is a categorical variable with three or more levels. So again, I'm going to specify the data frame, which is ANOVA underscore example. And to specify the column, you put a $sign, and I'm going to click on, or you could write out eyewear. Okay, now I'm going to hit enter. Oh my goodness, nothing happened. But it did. So it created a new model, which is eyewear 1. Okay. Now what you have to do to actually see what the model looks like in the output is you have to put in summary. Okay. Summary is the function. Put in some parentheses. Summary of what? Summary of the model. So you just put in the model name. In this case, eyewear 1. Again, you can name it whatever you want. You can name it literally anything. Okay. And then you hit enter and boom. This is what's called an omnibus test. It is just it's an overall one-way ANOVA. Okay. And so what you're seeing here is a couple of different things. Basically, a lot of this top row is talking about the between. Here, I'll go back to here we go. The between groups variance, a lot of that stuff is on the top row, sums of squares between, degrees of freedom between. And then the bottom row is a lot about the within groups variance, sums of squares within and degrees of freedom within. So you can see that this, for instance, is the sums of squares between. If you were to take that number and divide it by the degrees of freedom between, 325.3 divided by 2, you'd get the mean squares between. Hey, that's pretty sassy. Nice. Okay, how about sums of squares within? Because this residuals thing, or sometimes you'll see it called error, is actually mean squares within. Sums of squares within. 900.6 divided by the degrees of freedom within of 21 gives you a mean squares within of 42.89. Nice. Well, once you have the mean squares between, which is the between groups variance, and the mean squares within, which is the within groups variance, now you can find the F. Now you can find the F. So all you would do, if you were doing this kind of by hand, is you'd take the mean squares between and you divide it by the mean squares within. And 162.67 divided by 42.89 is 3.793. That is our F value. Okay, nice. Is it significant? Let's take a look at this p-value right here, 0.039. 0.039 is less than 0.05, which is our alpha level in this class. So it, in fact, is significant. This one-way ANOVA is significant. But what does that mean? So we know that overall, what this means is there is some kind of difference in screen time between the groups, glasses, contacts, or neither. Glasses, contacts, or neither. But this, what's called again, omnibus one-way ANOVA, the omnibus test is what gives us this F and P value. It's significant, but it doesn't tell us how, okay? It doesn't tell us exactly which of these groups, the group means of screen time, differ from each other. It doesn't tell us that. So we have to dig a little bit deeper. Now, what we're going to do is we're going to use another function called tapply or Tapley if you're if you're fancy. We can do Tapley. And what we're going to put in here is our dependent variable, which again was ANOVA example is the data frame. You put in a $sign and its screen time is then the column that we're looking for. So that's the dependent variable. Now you're going to put in a comma. I don't know why it's a comma and not a tilde in this one, but ANOVA example underscore example $sign screen time. That's saying, okay, look at my dependent variable. Now I'm going to input the independent variable, which is ANOVA example $sign eyewear, right? And now I'm going to say, hey, give me the means. Give me the means of each of the different eyewear categories in terms of their average screen time. Okay, so I'm going to click enter. And what we can see here now is it's giving me the group means. So this is the mean screen time for people who wear contacts, 8.125 hours. The mean screen time for people who wear glasses, 13.125 hours. The mean screen time for people who don't wear either of those things, 4.125 hours. Cool. So you get an idea of what the group means actually look like. And because the omnibus ANOVA was significant, it means that at least two of these means are different from each other. Now you could probably think, well, the largest value for screen time and the smallest value for screen time, those will probably be significantly different from each other. But we don't know if, for instance, people who wear glasses have a different overall screen time than people who wear contacts. Even though these numbers look different, we don't know if they're significantly different just by looking at the numbers. So you have to perform basically follow-up testing, okay? Follow-up testing. There's a few different types of follow-up tests. Basically, what we're going to do now that we've done the one-way ANOVA and found that there will be a significant difference, at least between two of the groups. It could be more than that. All of the groups could be different from each other, or two of the groups could be different. Like glasses and none could be different, but then glasses isn't different from contacts, and none isn't different from contacts. Or there could be basically any amount of differences or kind of not differences, significant differences between these groups. So, okay, I'm just going to tell you this. Hopefully you'll remember it. It's okay if you don't. There's a couple of different tests that we are going to do to follow up this one-way ANOVA to try to get at, well, which of these group means are significantly different from each other. There's two ways you can go about it. The first way is called a Bonferroni pairwise test. And that is usually used if you have a hypothesis about at least some of these groups being different from each other before you even conduct the ANOVA. So it's called a priori, before you even do anything. Just in a hypothetical sense, maybe there's a reason why we would think people who wear glasses would have a significantly higher amount of screen time than people who don't wear any kind of eyewear. And if you did have an idea, a theory about that, a hypothesis, then you would probably use the Bonferroni pairwise technique, which is what we're going to do. If you had no idea and you were just kind of looking around to see, hey, are any of these means going to be different? We don't actually know. You can do what's called a Tukey's HSD, Tukey's honestly significant difference test, which is called a post hoc or after the fact test. So we'll do both of those and just see how they're slightly different from each other. But anyways, all that to say, we've got these group means. We know because of the omnibus that at least two of them are different, maybe more, but we don't know which ones, so we have to follow it up. So you're going to type in pairwise dot t dot test, because what we're doing is essentially making a bunch of independent t-tests now, because you could do an independent t-test between contacts and glasses, contacts and neither, or glasses and neither, right? So we're going to do that basically. So pairwise t-test, and in there you put the dependent variable. So that's going to be screen time. Then you're going to put the independent variable. So that's going to be eyewear. And then you have to put this p dot adjust method. And it's right here if you click on it, but it's p dot adjust dot method. So p dot adjust dot method equals, and then you have to put in some quotation marks, Bonferroni, which is a fantastic name. Bonferroni. Okay. And once you do that, so this is a little bit of doing, but a dependent variable, independent variable, and this adjustment method, which is for a Bonferroni pairwise t-test. Let's click into that and let's see what happens. Okay, so cool. So it's given us essentially in this output, it's given us three different pairwise t-tests, independent samples t-tests, basically. Okay. And these values in this little table that it gives us, these are p-values, okay? These are p-values. So let's take a look. It's asking the question, do people who wear glasses and people who wear contacts have a significantly different amount of screen time on average? Well, that p-value is 0.425, which is way higher than 0.05, right? So that is not a significant difference. So we can go up here to people who wear glasses have an average of 13.125 hours of screen time. People who wear contacts and have an average of 8.125 hours of screen time. We have just discovered that those two means are not statistically significantly different because this is above 0.05. All right. How about people who don't wear either contacts or glasses versus contacts? So that's this 4.125 and 8.125 for the group means of neither and contacts. That's also not significant. 0.706 is higher than 0.05. Okay, so the only remaining test was people who don't wear any kind of eyewear versus people who wear glasses. That p-value is 0.036. That is significant. That's less than 0.05. So again, this value, 13.125 hours of screen time, is significantly higher than 4.125 hours of screen time. So we just found out people who wear glasses on average spend more time on screens than people who have no kind of eyewear. Nice. So that is how you conduct a one-way ANOVA. There's another way that we can get at the follow-up test, the pairwise test, which is you type in Tukey, Tukey, which is a fantastic name as well, HSD, and then in parentheses, you just put in the name of your model. So the model that I created was called Eyewear 1, but you could name it whatever you want. Eyewear 1. And if I hit enter, this is also pairwise comparisons. The difference is the Bonferroni method is actually the preferred method in a lot of cases if you have a priori hypotheses because it's a more conservative test. And what that means is it means that it's less likely that we will accidentally make a type 1 error because what you're doing here is you have three different pairwise t-tests. Every time you conduct a statistical analysis using an alpha level of 0.05, that introduces a 5% chance that you're making a type 1 error. So if you have three of those, the percentage chance of having a type 1 error increases for every test. So thankfully, Bonferroni is kind of a correction method that actually accounts for multiple tests and makes it more unlikely that we'll accidentally make a type 1 error because it actually makes it more difficult to get a p-value of less than 0.05. Tukey's HSD, Tukey's honestly significant differences, is not so conservative. So it's actually easier to find differences in group means, but that means that the chances that you make a type 1 error are potentially higher. So anyways, let's take a look over here. This is a slightly different output, but it's telling us the same thing. So glasses versus contacts, people who wear glasses versus people who wear contacts, the p-value is above 0.05. So that is not statistically significant. People who wear neither versus people who wear contacts. That is also above 0.05, so that is not statistically significant. People who wear neither glasses nor contacts versus people who wear glasses, that is below 0.05. So okay, so 0.03. So in this case, we actually just found the exact same thing. People who wear glasses have significantly higher amounts of screen time than people who wear neither types of eyewear. And the Bonferroni and the Tukey's HSD follow-up testing both gave us the same answer. Once in a while, though, the Bonferroni will say that something's not significant, and Tukey's will say that it is significant because it's a less conservative test. Anyways, all right. So, given that, I would like you to conduct an omnibus one-way ANOVA to see if people who wear glasses, contacts, or neither score significantly different in terms of average sleep. So let me know if there is a significant omnibus one-way ANOVA F-test. All right. Well, let's actually figure that out. So again, we're going to create a new model. Okay. And you could call it again, I don't know, I wear two or something like that. Um, Call it whatever you want, right? And then you put in this less than sign, and then a minus sign gives us kind of an arrow. AOV, I'm going to put in my dependent variable, which this time is actually going to be sleep, right? Sleep. Sleep is the dependent variable, and we're going to put in a tilde, and then we're going to specify our independent group, our independent variable, which is the eyewear group. And again, it's not going to do anything right away. You have to put in the summary of, in this case, I wear two, and it's going to give us, oh, I should have moved that way before, sorry. Um, it's going to give us this output. What this is telling us is that this is a significant omnibus ANOVA because it's less than 0.05. 0.001 is less than 0.05. So there is a significant difference somewhere in these groups when it comes to sleep, but we don't know where yet, right? So we can do tapply, and let's just take a look at the group means. So we're going to have the dependent variable, ANOVA example, dependent variable of sleep this time. And then we're going to have the comma, the independent variable. And then I want the means. So I just type in mean. Brilliant. Okay, so it looks like people who wear glasses are getting more sleep compared to people who have contacts or neither, but we don't know which of these things are significantly different, although we might be able to make some guesses similar to before. We don't know though. So let's do a Bonferroni pairwise. So you do pairwise.t.test, pairwise.t.test, and then you're going to, again, specify your dependent variable, sleep. You're going to specify your independent variable, eyewear, and you're going to do this p.adjust, p.adjust.method. P.adjust.method equals Bonferroni. Bonferroni, okay? And check this out. This is our follow-up testing. What this is saying is that if we take a look, it looks like there is a significant difference in sleep between people who wear contacts and people who wear glasses. People who wear glasses, people who wear contacts. So glasses is 7.50, contacts is 5.75. So that's a significant difference in average sleep. 1.0 is as high as it goes. That's way higher than 0.05. So people who don't wear any eyewear and people who wear contacts, 5.75 and 5.25, those are not statistically significantly different because this value is above 0.05. That makes sense. And then people who don't wear either, and then versus people who wear glasses, that is also below 0.05. So that is significant. So glasses versus none, that is significant. So what we just found is that people who wear glasses have a statistically significantly higher average sleep than people who wear contacts and people who wear neither. But there is no statistically significant difference between people who wear contacts and people who wear neither in terms of their average sleep. Okay? Hopefully that was interesting, and thanks for listening. I'll see you in the next video.